Hi, Math 0232 students. I am going to make a video because I had some students that asked a couple questions about some things from 1332, and I'm just going to address those really quick. This isn't going to be a beautiful video because I'm not going to take the time to edit it, but I'll do my best to make sure it's comprehensive and clear, even if not perfect. Okay, so it was the first thing that was asked about was activity 4A, which has to do with independent events. And then there's a homework question that has some problems on independent events and another problem about dependent events. And then there's also was some questions on some set notation and some set theory things. So I'm going to try to cover all three of those. All right, so on this first one, it asks, if you roll a die, what are the possible outcomes? Well, of course, when you roll a die, you could have, anywhere from a 1 up to a 6. So if you look at the sides of the die, they've got the dots on them. If you wanted to write it out with numbers, it would be anywhere from 1 to 6. Okay, so 1, 2, 3, 4, 5, 6. Those are the outcomes of a single die. If we flip a coin, of course you can get heads or tails on most standard coins. So those are the possible outcomes. Now, if we're looking at two events, and usually what we're saying with two events is we're saying one occurs, then the other occurs. So it could be flip the coin again. That's the typical way. So when we're talking about independent versus dependent, independent is where whatever you do on the first occurrence or the first trial does not affect the second trial. So what are some examples of that? Well, a die is one example, or dice. A coin. Or another one that's common in a lot of statistics classes is, or stats and probs class, is a deck of cards, or drawing things out of a hat or out of a bucket or something like that. And those things can either be independent or dependent. So if you have cards, then they are independent. Remember, we're talking about independent. Then they're independent if you replace after each draw. So what we're talking about is you don't want to change the possible outcomes if you want to keep the consecutive trials independent. So if you take a card out, that's going to change how many cards there are and what types of cards there are. For instance, if you pull out a 5 of hearts, then you have 1 less 5, and we also have 1 less heart, depending on how you want to look at it. But you have 1 less card. Instead of 52 cards after you draw, you only have 51 cards. So if you want it to remain independent, you have to replace that card and reshuffle in order to keep that independent. And the same thing if you're talking about, like, say, colored balls in a bucket. Again, it will stay independent if you replace, or if there's replacement between each draw. So between draws. Okay, so if you roll a die, what is the probability of a 2? If you flip a coin, what's the probability of heads? Well, the probability of rolling a die and getting a 2 is, out of those, if you remember up here, out of these 6 things that you can get, one of them is a 2. So 1 of the 6 sides of the coin is a 2. So you have a 1 out of 6 chance that you're going to get a 2. If you flip a coin, what's the probability of getting a heads? Well, you can get heads or tails. So the probability of getting a heads is 1 out of 2 ways that you can flip that coin. So now we're going on to the 2 events or 2 things happening one after another. It asks if you roll a die and you flip a coin. It doesn't matter if you do them at the same time or you do one and then the other. We'll think of it as rolling the die and then flipping the coin. Does the occurrence of a particular outcome on the die affect the outcome on the coin? And the answer to that is no. I mean, the die and the coin don't have anything to do with each other. A lot of times in statistics we'll say they don't have memory. They don't have brain. Like the die doesn't know what the coin did and the coin doesn't know what the die did because they don't have memory or a brain to know what the other one did. So every time you pick up the die, it's reset basically, and the same thing with the coin. Every time you pick it up, it's reset. Even if you get 3 heads in a row, it doesn't matter. The 4th time, you're not more likely to get a tail. Every time you pick up the coin or you roll the die, it's reset to 1 out of 6 for the die and 1 out of 2 for the coin. So now let's go on to the second page of section 4A. All right, so the first question on this page asks, if you roll 1 die and you flip 1 coin, what are all the possible outcomes? Well, as far as the die, you can either get a 1, a 2, a 3, a 4, a 5, or a 6. With those 6 choices, with each of those, you could roll a heads. So 1 heads, 2 heads, 3 heads, 4 heads, 5 heads, 6 heads. But you could also roll a 1 through 6 and get a tails. So these are all the possible outcomes that could happen. You could get a 1 through a 6, and you could get any of those with the heads, or you could get any of those with the tails. So there are 12 possible outcomes that could happen because there's 6 outcomes for the die, and then there's 2 outcomes for the coin, so 6 times 2. So if you roll 1 die and flip 1 coin, what is the probability of rolling a 2 and flipping heads? Well, that's this possibility here. Whoops, just a second. I can't get the color to change. So that's this right here. We've got 1 way out of the 12 ways. So we have a 1 in 12 chance that we're going to get a 2 and a heads. And again, the Y is because there's 1 way to do that out of the 12 different ways. So it says, consider your answers to 3 and 6. How are the answers of each of these 2 independent events related to the probability of the events both occurring? Again, you have 1 out of 6 ways of getting a 2 on the die, and then you have a 1 out of 2 chance of getting a heads. So this is a 1/6 chance of rolling a 2. It's a little confusing because we're rolling a 2 and then there's 2 things on the coin. But 1/6 chance of rolling a 2 and then a 1/2 chance of rolling heads. Well, 1/6 times 1/2 is 1/12. 6 times 2 is how we get 12 things happening. We're going to skip this one because I don't have that info readily available. So if you roll 1 die and flip 1 coin, what is the probability of rolling a 2 or flipping heads? Now we're talking about something a little bit different. We're talking about an or instead of an and. So we're not saying we need a 2 and a heads. We're saying we want a 2 or a heads. So if we go back to our original setup here, what we mean by the or is that we can get either or and we will count it. So in this case, if it's got a 2 or it has a heads, we're going to count it. So in this case, we've got these two twos, or flipping a heads, well, that's all of these. Or if we wanted to do it kind of in one fell swoop, we could have circled it like this. Here's all the heads. And here's all the twos. Now the thing with this is, when we're doing an OR, you don't want to double count. So you have a 2 out of 12 chance of rolling a head, or I'm sorry, of rolling a 2, and then you also have 6 ways to roll the head. But if I do that, if I say 2 plus 6, then I'm going to end up with 8 out of 12 ways. But that's not true, because when we've done that, we've counted this one twice. And so really what we have is we have 2 out of 12 ways to roll a 2. And then we have 6 out of 12 ways, but we've already counted one of them. So that's what this formula right here means. You're going to take out anything that you double counted. So this that we double counted, we want to take out. So a lot of times I tell students, don't add it in. Just do 2 12s plus 5 12s, or just count how many there are. There's 1, 2, 3, 4, 5, 6, 7. There's not 8, there's 7. So there's the 6 here plus the additional 1, or there's the 2 here plus the additional 5, however you want to think about it. But we don't want to count the 2 of heads twice, because that's still just one of the possibility. It just happens to have both of them in it. So OR means you're going to count it if it has one of the characteristics or the other characteristic, but if it has both characteristics, you have to take that out. So probability of A, 2 12ths head, probability of B, 6 12ths heads. I'm sorry, this one was 1 6 2, and this was, hold on, let me back up out of here. Let me go back to the original. Okay, so the probability of rolling a 2 out of these 12 possibilities was 2 out of the 12 ways. And then the probability of getting a heads was 6 out of the 12 possibilities, but we want to make sure we subtract out the one that would get double counted if we did it like that. Or you could just think of it as 1, 2, 3, 4, 5, 6, 7 out of 12 to begin with. Just don't double count it. That way you don't have to subtract it out. But this is the official formula for it. You could write it as 1 6 plus 1 half minus 1 12. I think that gets a little bit more confusing because you have different denominators. I think it's easier to think of the common denominator first if you are going to use the formula. So my biggest recommendation on this is draw a picture if you can, because when you draw the picture, you can see how many things are going to fit the category. So in this case, 2 or heads, well, that would be, again, these 6 that have heads and these 2 that have 2s, and that gives us 7 out of the total 12. If you have that picture, it's a lot easier to see. So now, remember, I'm just kind of trying to go over the things that were asked of me from material from 1332, so this might be just a little bit disjoint. The next thing that I had someone bring to me was this following. So this was like an additional handout that you had with lessons 4A and 4B. And so it has the AND events, the OR events, the dependent events, and then the conditional probability. So this again is the probability of A and B if they're independent, A or B if they're dependent or independent, and then we have dependent events, and then we have conditional probability. So we have some examples here that we'll go through. So what's the probability that a U.S. male will die from cancer if he's been diagnosed with cancer? Oh, geez, I have to find the information for that. Just a second. Okay, so now what we're going to do is we're going to look at this table in order to do this. Now, the general rule for conditional probability is that the probability of A given B is the probability of A divided by the probability of B. Now, sometimes if we have the actual numbers, you can throw out some things. So for instance, these are in percentages, so we can't really do it like that. But if you actually have numbers, the given B part means that that's the only thing you're given. So you could just use that given as your bottom number. What it really saves is it saves you having to divide a fraction by a fraction. But in this case, it's not really that much helpful. So we'll just go ahead and use the formula. So the probability that a male is going to die from cancer, given that they have cancer, it says that it's 1 in 5. So that would be 1/5. And then the probability that they have cancer is 1/2. They're using decimal percentages here too. If we use the fraction, it's 1/5 divided by 1/2, but those look like they're approximated. So for instance, they said 41.6% is 1 in 2, which isn't really right. It's more like, that would be like 50%. So let's back up a bit. I think we'd be more accurate if we use the percentages. So the probability of dying from cancer is 19%. So that would be 0.19. And then given that they have cancer, that's 41.6. So 0.416. So what we're saying is 19% of the 41% will die from cancer. So if we divide that, it's giving you your chances overall before if you know that you have cancer, what are the chances of dying from it? So we're going to divide those, and you just want to grab your calculator. You don't want to try, there's no way to really do that in your head. So do 0.19 divided by 0.416. And that comes out to be approximately 0.45, and then it's like 673. So if I round that third decimal, 4567 would round to 4.57. Okay, so that's what we got. And then there was a little bit more after that, but if we're trying to round to the third decimal, this 7 tells that 6 to go up. Now, the next one says, what's the probability that a U.S. female will die from lung cancer if she's diagnosed with lung cancer? So now we're only going to look at lung cancer. We're not going to look at all cancer, and we're going to look at females. Okay, so now I went over and pulled the female data. So this is males, this is females. So I'm going to go over here to the females, and it says lung cancer if have lung cancer. So we've got lung cancer, the alphabetical is right here. So we're looking at the percentages. That's the easiest, I believe. So we're going to say 3.8% divided by 5.9%. So you have a 3.8% chance of dying from lung cancer, and then the chances of developing are 5.9%. So this would be 0.038 divided by 0.059. So given that the person has lung cancer, what are the chances that they will die? So and of course that's going to increase your chances of, if you know that you already have it, you have a lot higher chance of dying from it, of course. So we do 0.038 divided by 0.059, and we get 0.644. Again, this is the chances of dying from it knowing that you already have it. So about a 64% chance of dying from it if you've been diagnosed with it. Same thing up here. For overall cancers, about a 50% chance of passing away from it, given that you have been diagnosed with cancer for a male. But that's any cancer. So now it says, what's the probability that a U.S. male will die from lung cancer if he's diagnosed with lung cancer? So again, we have to, on the bottom, you're going to have the probability that they actually have it. And then on the top, the probability that the male dies from it. So now we're looking at males, and we're looking at this number and this number. So the risk of dying goes on top. That would be the 4.4. And I'm actually thinking to myself, we really don't need to shift the decimals because we're shifting the decimals on both of them. So you could just do 4.4 out of 6.3. I'll do it the way I've been doing, but just know that you really don't have to shift the decimals because they're both would be shifted. Okay. So then we have 0.044 out of 0.063. So if we divide those, we get 0.698. So it looks like males have a slightly higher chance, because these are the same thing except for male or female. So a slightly higher chance of a male dying from lung cancer if they've been diagnosed with lung cancer. They have a 70% chance almost, whereas women only had a 64% chance. And again, all three of these examples are the conditional probability, A given B. And the first thing that it mentions, that goes on top. The second thing that it mentions, that goes on the bottom. So the first thing is the numerator and the second thing is the denominator in general. That's a little bit oversimplification, but in general. Okay, so let's go on to the next thing that I was asked about. And that was a question out of the online homework. So these are problems on independent and dependent events again. So in this one it says that you have a vending machine containing jelly beans. Will only dispense one jelly bean at a time. There's 12 red, 8 yellow, 4 green. And the yellow jelly beans have a rotten egg flavor, so of course you don't want to get that one. I'm going to draw a picture of this really quick. Okay, so here's the jelly beans drawn out. Again, we have 12 red, 8 yellow, and 4 green. So the first question says, what's the probability of getting a red jelly bean on the first draw? Well, we have 12 red jelly beans out of 24, so it would be 12, oops, let me change colors here. It would be 12 out of 24, or 1 out of 2, or 0.5, or 50%. If you want to get the 12 out of 24 on your calculator, you can use your fraction function on your calculator, or you can do 12 divided by 24. That'll give you the 0.5. Then we can shift that decimal over 2 spots to get 50%. So now the second one, so this is just one single event. So we don't have to worry about whether it's independent or dependent because it's just one single event. But now we're going to go to a situation where it says, let's say you did get a red jelly bean on the first draw. What is the probability that you will then get a green on the second draw? Well, we're assuming you're not throwing the jelly beans back in the bag. When you take jelly bean out, you're eating it or giving it to someone. And so it changes on this because now we have one less jelly bean. So now the probability that you get a green on the second draw is 4 out of 23. Because you don't have 24 jelly beans anymore, and we're looking at the green ones. So we're looking at these 4 green ones out of the 23 that are left. So 4 out of 23 as a percent, if we divide that, 4 divided by 23 would be approximately 0.1 174 or 17.4%. Looks like the person that sent this to me may have thrown out all of the red jelly beans. It just says you got a red on the first draw. So it doesn't mean we throw out all the reds. We just throw out that one red that we drew. So now let's finish up with this last one. It says, if you'd gotten a yellow on the first draw, would your answer to part B be different? Yes, it would. Because, actually on this one, if you drew a yellow, no, that wouldn't change your answer. So what that would have changed, it said if you would have gotten a yellow on the first draw. So let's go back to our original starting bag of jelly beans, or vending machine of jelly beans. So if we've got, 24, and instead of a red one on the first draw, you took out a yellow one. That wouldn't change this. You still would have a 4 out of 23 chance of getting a green jelly bean. Because you still have 4 green jelly beans and you still have only 23 jelly beans to pick from. Now, let me throw in an extra question. I'm assuming maybe it went on to do something like this later in the homework. I don't know for sure. So an extra problem, what would be the probability of getting a yellow or let's stick with green. Probability of a green after picking a green. Now that would change things, because if we reset this back to our original bag of jelly beans and we said on the first draw, instead of getting a red or a yellow, let's say we got a green. Well, that takes out 1 green jelly bean. So the probability of getting a green, again, we still only have 23 jelly beans because we've taken 1 out. But now, in addition to that, we got a green the first time, so we've only got 3 green jelly beans left because we've removed a green one. Before we picked a red and then a green and a yellow, then a green. This time we're doing green and then a green. Well, because we already took a green out, we've only got 3 green left. So that would be 3 out of 23. So you have to look at what's left in the bag compared to what you started with. So we've taken 1 green jelly bean out. That changes the bottom number to 23. Took 1 out. And then we also took out, the one took out was green. And so now we're down to 3. So 3 out of 23 would be 0.1304 approximately. And then that would be 13.0%. So the chances of getting a green after you've already taken out a green are lower than getting a green after you took out one of the other colors. So, getting a green after already getting a green is a lower chance. And that's because these are not independent events. When you're leaving a jelly bean out, that's affecting the next draw. So these are not independent events when you take out a jelly bean and you don't put it back in. It's not like a die where it gets reset every time. This time the jelly beans are going down as you draw them out, and different colors are going down if you pick out 2 of the same. So if you get a green and then a green, or if you get a red and then a red, that's going to not only change the total number, but it's also going to change the color that you're looking for. So now the last question that I had was on some of the set notation with the unions and the intersections. So we'll go on to that. So these are the different theory symbols that it looks like were used. I pulled this off of a resource out of the internet, except it doesn't look like this one is being used, the superset. But I did see, I think, all the other ones in the homework questions, or in the worksheet questions. So this was the sheet that was shared with me. Hold on a second. I can get it to paste into here. Okay. So I'm just going to go through this real briefly. Okay. So this first one, it asks to determine if each is true or false and justify your answer. This first one doesn't have a symbol on it. I don't know if it's a typo or something. I mean, I'm just going to throw in a symbol. Let's say it said, determine if it's true or false. So it's got to be some sort of a subset or equivalent or something. So let's say we do this one. Okay, so that would be a subset. So a subset means that this first set is completely included in the second set. So our first set here is a 5, and 5 is included in this set. So this is true. Because 5 is a member of or in this set is within this set. So 5, the only element in this set, is included in this set because there's a 5 there. Now, in this case, we're talking about equivalent. There's actually not a symbol over here for that. But equivalent just means that you could pair them up. Okay, so they have the same number of items in it. So equal means they have to be have the same things in each of them, but equivalent just means they have to have the same number of things. So the same number of items in the set. So in this case, if we kind of pull these out, days of the week would be Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. And then 2, 4, 6 to 14, 2, 4, we kind of write them right underneath each other, 6, 8, 10, 12, 14. We can see these two sets both have 7 in them. So we could match 1 to 1. We could say we'll let Monday be 2, Tuesday be 4, Wednesday be 6. They would have a partner. All of them would have a partner. So are they equivalent? Yes, they are equivalent. They're not equal. Obviously, this is days of the week. This is numbers, even numbers. They're not the same set, but we call them equivalent if they have the same number of things in them. So here they're using that equal symbol. So equals is different than equivalent. Equals means they're exactly the same. So these two sets would be equivalent, but they are not equal. So we would say equivalent, they have the same number of sets of items in there. Here they have 4 items in the set, 2 items in the set. They're equivalent, but not equal. Not the same. So same number, but not same items. Let me back that up. So equivalent because they have the same number, but not equal because equal means the same elements, the same members. Okay. Now this one is again the subset, so that's the same one as up here. So we're looking for is every set or every element of this set included in this set. So is there a D? Yes, there's a D. Is there an E? Yes, there's an E. Is there an F? Yes, there's an F. But is there a G? No. Okay, so this is false because the second set does not have a G. So in order for this to be a subset of this, that means that I should be able to find everything that's in here. And there is no G over here, so it's not a subset. So if you think of it like a Venn diagram, I know you do Venn diagrams down here, but like if we look at the original set or the second set, A, B, C, D, E, F, could you circle some of those and get a subset? D, E, F, G. No, because I couldn't get a G because there is no G in here. So the second set, A, B, C, D, E, F, Doesn't have a G, so I couldn't make a subset out of it. Okay, so in this one, this is called a proper subset. So that means basically the same thing as up here, except it also can't be exactly the same subset. So you can actually say that a set is a subset of itself. So they could have like the same number of elements in it. But a proper subset means the one that's in the front has smaller number of things in it than the other one. So here we've got 3, 4, 5, and here we have natural numbers less than 6. So let's write that out. So we've got 3, 4, 5, and then we have natural numbers that are less than 6. That would be 1, 2, 3, 4, 5, and 6. So is this a subset of this? There's a 3, there's a 4, and there's a 5. So yes, it is a subset, and then it's also what we call a proper subset if it has a smaller number than the other set. So with this symbol, see this little subset symbol? It could be a subset or equal to it. Here it has to strictly be a subset. So since this only has 3 items and this has 6, again, let me draw this out. So the original one, the bigger one, 1, 2, 3, 4, 5, 6, we could circle 3, 4, and 5 as like a subset, and we still have elements left over. So that makes it a proper subset, because you're not just recircling all 6 of them. So a proper subset has to have less elements than the second set has. And then this one says 14 is not an element of. So E is a member of or is an element of. I like to think element because it kind of looks like an E. So is an element of. Well, 14 is not an element of 1, 2, 3, 4 all the way up to 40. Yes, it is, because 1, 2, 3, 4 all the way up to 40 means even though we have these ellipses in here, you still have all the numbers up to 40. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and so on, up to 40. Well, 14 is in there. Just because they didn't, just because they did the dot, 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 you would still come across 14 if you did all the numbers, all the whole numbers up to 40, or all the counting numbers up to 40. All right, so a couple more here and we'll call this video done. So here are our defined sets. We have U, which is A, B, C, D, E, F, G, which is everything that's in any of these, and then we have a subset A, B, C, D, C, D, E, F, and A, E, G. So if we want to do a union, let's back up and talk about unions and intersections. So talk about it in a way that we're familiar with streets. So let's say this is Main Street, and say this is 5th Street or 5th Avenue. Okay? If you tell someone that you're going to meet them at the intersection of Main Street and 5th Avenue, that's this area right here. It's where they cross. So an intersection is where they cross. Okay, it's the crossing. It's what they share. When we're using the words and or, an intersection is and. Okay, so the word for that is and. I'm going to meet you at 5th and Main. That's right here. Okay, that's an intersection. Now, if somebody says, I'm going to meet you on 5th or Main, that means they could be anywhere along this road or anywhere along that road. If you were trying to meet them, that wouldn't be very helpful. That's an or. You could be anywhere along Main Street, anywhere along 5th Avenue. So say you're going to meet for a parade. You'd have no idea where they were. They could be anywhere along Main Street, anywhere along 5th Avenue. You might be able to find them if you wander up and down Main Street and up and down 5th Avenue, but who knows? So a union is all of both, basically. And that word that matches with that is or. So Main or Fifth Avenue. So if we look at these, first one says A union B. So that means we want anything that is in one or the other or both. So all of both. So A has A, B, C, D. And then B has C, D, E, F. Well, we've already have C and D, so we don't have to list them again, but we do need to list the A and the F, or the E and the F. So A, B, C, D. C, D's already been listed. E, F. That's everything that's in one or both. This little mark right here means like the opposite of. So let's figure out what it is first, and then we'll go back to what the not part means. So B intersects C. So what do B and C have in common? They don't both have A. They do both have E. That's it. So B intersects C is only G. But if we want to do not of that, then that would be anything in B and C but not G. So A, C, D, E, F. Okay, so the things that are in one or the other but not in the intersection. That gets a little confusing, but my recommendation is do the inside part. Do the B intersects C first, and then that tells you what you have left over for the not. The not is everything that G is not. Okay, now this one we have to do in a different order because this one doesn't have the parentheses around it. It just has the not on the C part. So we have to figure out what not C is first. So not C would be anything that's in the union or in the like the whole set, like everything available, but is not in C. So A, we would do B, C, D, and F. So everything that's available. So this is like everything that's available, but we want everything that's not in C. Well, A is in C, so we don't list that. E is in C, we don't list that. G is in C, so we don't list that, but we list the B, C, D, and F that are not in C. And now we want to do A intersect not C. So that would be A, which is A, B, C, D, intersect not C, that's B, C, D, F. So anything, remember intersection is where they cross, what they share, what they both have. So Fifth and Main meet here. This is the only place where it's both Fifth and Main. So what is in both of them? Is A in both of them? No. Is B in both of them? Yes. Is C in both of them? Yes. Is D in both of them? Yes. Is F in both of them? No. F is only in not C, and A is only in A. So the intersection is B, C, and D. That's what they both share. And now we're going to do this in terms of a Venn diagram. So A intersects C means those things that are both in A and C, or the number of elements. So A and C. So sometimes color is helpful. So here's A, and here's C. So how many things are in both of those? It's not just these 8 or just these 5, it's actually both of these. So the 8 and the 5 are in the red circle and the blue circle. So there's actually 8, 9, 10, 11, 12, 13 things. So this is 13. Now we're going to do union. Remember, union is anything that's in one or the other. Like it's both of them. Anything that's in one and also in the other. All of both. So if we go here and we look at B, that's this one. But we don't want to double count anything. So, and C, that's this one. So I'm going to count anything that's in one or the other, but don't double count the 8 and the 6. So we have 7 plus 3 is 10, 18, 19, 20, 21, 22, 23, 24, 29, 33. I'm doing the 7, the 3, the 8, the 6, the 5, and the 4. Anything that's in one or the other, but don't double count these ones that overlap, the 8 and 6. So 7 plus 3 plus 8 plus 6 plus 5 plus 4. All right. What was that? 33. Just a second. I want to get that on there without having the circles there. So 33. Okay, so not A. So anything that's in A, we're not going to count. Okay? Don't count any of these, but count anything else. 3, 6, and 4 for 13. The union is like everything. That's like the whole, everything possible. So we're just going to add up all these numbers, but don't double count anything. So 2 plus 7 is 9, 10, 11, 12, 17, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Oh shoot, I didn't see that one out of there until just now. We might have to go back and adjust something because I didn't see the one that was out here at first. Okay, and then A intersect B intersect C. That's actually one of the easiest things where all the circles intersect. That's right here in the middle. So where the A circle, the B circle, and the C circle intersect. That's just 8. Hold on. Let me make sure that we didn't mess anything up by missing this. So not A. Not A. I think we're okay with everything except for the not A. Not A. Okay, so here's A. Everything that's not A, I said 3, 6, and 4 for 13, but I missed this one out here. So it's actually 14, not 13, because I missed the one that was out here. So not A would be these 3, this 6, this 4, and then this 1 that was out here, but not in any of the other ABC sets. So that's all I have. I hope that some or all of that helps, and let me know if you have any questions when we have class next.